Hi friends, welcome back to our YouTube channel. Today we have to discuss about Mod 6 Synchronous Down Counter in Digital Electronics course, Digital Logic Design course and Switching Theory and Logic Design course. To design Mod 6 Synchronous Down Counter, we have to follow 6 steps. The first step is determine how many number of flip-flops are required to design Mod 6 Synchronous Down Counter and which flip-flop we have to use. This is the first step. We already know that Mod N counter contains n states. So in the same way, Mod 6 counter contains 6 states. Now, once we are knowing the number of states in Mod 6 Synchronous Down Counter, next we have to find out how many number of flip-flops are required to design Mod 6 Synchronous Counters. Number of flip-flops required can be calculated by using a formula. Capital N less than or equal to 2 power n, where capital N is nothing but number of states that are present in Mod 6 Synchronous Counter and small n is nothing but number of flip-flops required. Here, if n is equal to 1, then 6 less than or equal to 2 power 1. That means 6 less than or equal to 2. So this is false. Next, if n is equal to 2, then 6 less than or equal to 2 power 2. That implies 6 less than or equal to 4. That is also false. If n is equal to 3, then 6 less than or equal to 2 power 3. That implies 6 less than or equal to 8. So the condition is true. So therefore, when the condition is true at n is equal to 3, therefore, so number of flip-flops required can be denoted by small n, that is equal to 3. Next one is maximum count value. Maximum count value is equal to capital N minus 1. Capital N is nothing but number of states. So that is 6 minus 1, that is equal to 5. Maximum count value is 5. Total 6 states are there. So starting with 0 and ending with the maximum count value, that is 5. So here 0 to 5. Total number of states is 6 states. Next one, we have to use either JK flip-flop or T flip-flop to design mod 6 synchronous down counter. Here we have to use T flip-flop. We have to use T flip-flop to design mod 6 synchronous down counter. So this is the first step. In the first step, we have to know about how many number of flip-flops are required to design mod 6 synchronous down counter, that is 3. How many number of states are present in mod 6 synchronous down counter, that is 6 states starting with 0 and ending with 5. To design mod 6 synchronous down counter, we have to use either JK flip-flop or T flip-flop, but in this problem I am using T flip-flop. Now, we can go for step 2. In the step 2, we have to write the excitation table of T flip-flop because the decided flip-flop is T flip-flop. Therefore, we have to write the excitation table of T flip-flop. In the excitation table, the inputs can be taken as Qn and Qn plus 1. Qn is nothing but present state. Qn plus 1 is nothing but next state. These two can be taken as inputs and the output is, that is excitation input, that is T. Here with how many number of inputs are there? 2 inputs are there. With the 2 inputs, how many number of possible combinations are there? 4 possible combinations, that are 0 0, 0 1, 1 0, 1 1. Next, how to write the T value? T value is equal to 0 when both inputs are same. T value is equal to 1 when both inputs are different. Now, both inputs are same, that is we have to write 0. Both inputs are different, we have to write 1. Both inputs are different, we have to write 1. Both inputs are same, we have to write 0. So how to write the excitation table? That can be explained in T flip-flop using NAND gate and T flip-flop using NOR gate. Please refer that video. In that video, I am explaining how to write the excitation table from the characteristic table. Now, once we are writing the excitation table of T flip-flop, next we can go for step 3. In step 3, we have to draw the state diagram of mod 6 synchronous down counter. Total how many number of states are there? 6 states are there. 1, 2, 3, 4, 5, 6. These are the 6 states are there. Each state can be represented by using how many number of bits? So that is 3 bits, because we have to use 3 flip-flops to design mod 6 synchronous down counter. Each flip-flop can store 1 bit. So for 3 bits to store, we have to use 3 flip-flops. So each and every state contains 3 bits. Now this is 0 state, 1 state, 2nd state, 3rd state, 4th state and 5th state. So 0 state can be represented by using 3 bits, 0 0 0 0. 1 state can be represented by using 3 bits, 0 0 1. 2 state can be represented by using 3 bits, 0 1 0. 3rd state can be represented by using 3 bits, 0 1 1. 4th state can be represented by using 3 bits, and fifth state can be represented by using 3 bit. Now it is a down counter, so that starting with the 0 0 0 state, then immediately it goes to 1 0 1 state. Then it can goes to 1 0 0 state. Then it can goes to 0 1 1 state. Next it goes to 0 1 0 state. Next it can goes to 0 0 1 state. Next it can goes to starting state 0 0 0 0. So this is the starting state. Okay. So this is the state diagram of 3-bit mod 6 synchronous down counter. Next, now in step 4 we have to write the circuit excitation table. In the circuit excitation table, the first column represents the present state, the second column represents the next state, and the third column represents the excitation inputs. T1, T2, T3 can be called as excitation inputs. In the present state, there are 3 bits are there, Q1, Q2, Q3. In the next state, 3 bits are there, Q1 plus, Q2 plus, Q3 plus. For Q1 present state, the next state is Q1 plus. For Q2 present state, the next state is Q2 plus. For Q3 present state, the next state is Q3 plus. When the present state is Q1, Q2, Q3, the next state is Q1 plus, Q2 plus, Q3 plus. Now, in each and every state of state diagram that can be represented with the 3 bits, the MSB bit, so the MSB bit can be taken as Q1 and the LSB bit can be taken as Q3 and the middle bit can be taken as Q2. As your wish, you can take MSB bit can be taken as a Q3 and LSB bit can be taken as Q1. Your wish, there is no problem at all. I am considering LSB bit can be taken as Q3 and MSB bit can be taken as Q1 and the middle bit can be taken as Q2. Okay. Now, first starting with present state. In the present state, the state diagram starts with the 0 state. So 0 state contains 3 bits that are 0, 0, 0. What is the next? When the present state is 0, 0, 0, what is the next state? The next state is 1, 0, 1. 1, 0, 1. Now, 1, 0, 1 can be taken as present state. What is the next state? The next state is 1, 0, 0. Next, 1, 0, 0 can be taken as present state. What is the next state? The next state is 0, 1, 1. Now, 0, 1, 1 can be taken as present state. What is the next state? The next state is 0, 1, 0. Now 0, 1, 0 can be taken as present state. What is the next state? The next state is 0, 0, 1. Now 0, 0, 1 can be taken as present state. What is the next state? So that is 0, 0, 0. So starting with 0, 0, 0 as present state, the next state finally it can goes to the 0, 0, 0 state. Okay. We already know that with the 3 bits, how many number of possible input combinations we are getting? 8 possible combinations we are getting. That means 2 power 3, 8. But here only 6 possible combinations are there. The remaining possible combinations, okay, so that are 1 1 0 1 1 1. The next state is don't care because they are invalid states. These two states are called as invalid states. Invalid states that cannot be represented in state diagram. Okay, invalid state because in mod 6 synchronous down counter state 6 and state 7 are invalid states. Invalid states, they can be represented with don't guess. They can be represented with don't guess. Don't care means cross mark. Okay. For 1 1 0 present state, the next state we do not know. They can be represented with don't care. For 1 1 1 present state, there is no next state that can be represented with don't guess. So if you wish, you have to write these two rows in the circuit excitation table. If you do not wish, you do not mention these last two rows. Okay, as your wish. Now, how to fill out T1, T2, T3 columns? For filling out T1 column, we have to consider Q1 and Q1 plus as inputs and write the T1 outputs by using this excitation table. Okay, first Q1 value 0, Q1 plus value is 1. Both inputs are different, so then T value is 1. Q1 value 1, Q1 plus 1 value is 1. Both inputs are same, our output is 0. Here 1, here 0. Both inputs are different, output is 1. Here 0, here 0. Both inputs are same, then T1 value is 0. Here 0, here 0. Both inputs are same, T value is 0. Here 0, here 0. Both inputs are same, then T1 value is 0. Next, here 1, here don't care. So one of the input is don't care among these Q1 and Q1 plus. So then output is also don't care. Here 1, here don't care. The output is don't care. Next, for filling out T2 column, we have to consider Q2 and Q2 plus as inputs. So here Q2 value 0, Q2 plus value is also 0. Both inputs are same, T2 value is 0. Here 0, here 0. Both inputs are same, T2 value is 0. Here 0, here 1. Both inputs are different, T2 value is 1. Here 1, here 1. Both inputs are same, so then T2 value is 0. Here 1, here 0. Both inputs are different, T2 value is 1. Here 0, here 0. Both inputs are same, T2 value is 0. Here 1, here don't care. One of the input is don't care among the two inputs. The output is also don't care. Here also don't care. Next, for filling out T3 column, we have to consider Q3 and Q3 plus as inputs. Q3 value 0, Q3 plus value is 1. Both inputs are different, then output is 1. T3 value is 1. Here 1, here 0. Both inputs are different, then T3 value is 1. Here 0, here 1. Both inputs are different, its value is 1. Here 1, here 0. Both inputs are different. Its value is 1. Here 0, here 1. Both inputs are different. Its value is 1. Here 1, here 0. Both inputs are different. Its value is 1. Here 0, here don't care. One of the input is don't care among the two inputs. The output is also don't care. Here 1, here don't care. Here also don't care. So this is the circuit excitation table. Next, we have to find out the simplified Boolean expression for T1, T2, T3 excitation inputs using 3-variable Carnot map, because the present state contains 3 bits, so that we have to use 3-variable Carnot map. In that 3-variable Carnot map, so 110 combination, 111 combination always contains the don't cares. So that can be shown in step 5. So we have to write the 3-variable Carnot map for 3 excitation inputs T1, T2, T3. First, for finding out the simplified Boolean expression for T1, we have to identify the T1 column. In that T1 column, only consider ones and don't cares. Here 1 is there. The corresponding input combination is 0, 0, 0, 0. Next, here 1 is there. The corresponding input combination is 1, 0, 0. Here 1, here 0, 0. We are placing 1. Next one, don't care is at 1, 1, 0. So here 1, here 1, 0. This is 1, 1, 0 cell. We are placing don't care. Here don't care is there. The corresponding input combination is 1, 1, 1. Here 1, here 1, 1. At 1, 1, 1 cell, we are placing don't care. First, we have to concentrate only on ones. Okay. So now these two ones can be formed as a pair. For this pair, the horizontal side contains 0, 1. It belongs to the Q1 variable. Both bits are different. Simply we have to ignore the Q1. In the column side of the pair, we are containing 0, 0, 0. This 0 belongs to Q2. This 0 belongs to Q3. So Q2 value is 0 means Q2 bar, and Q3 value 0 means, so that is Q3 bar. The simplified expression we are getting for T1 is equal to Q2 bar, Q3 bar. Next, this is the Carnot map for T2. Now identifying T2 column and identifying ones and don't cares. Here 1 is there. The corresponding input combination is 1, 0, 0. Here 1, here 0, 0. We are placing 1. Next, here 1 is there. The corresponding input combination is 0, 1, 0. So here 0, here 1, 0. At 0, 1, 0, we are placing 1. And this don't care is there. The corresponding input combination is 1, 1, 0. Here 1, here 1, 0. We are placing don't care. Here don't care is there. The corresponding input combination is 1, 1, 1. Here 1, here 1, 1. So at 1, 1 cell we have to place a don't cares. Okay. So here, by observing this one and this don't care can be formed as one pair. Next one, in the corners are there, this one and this don't care also can be formed as a pair when we are folding the Carnot map from right to left in the middle. Okay, so now this don't care and this one can be formed as a pair. Okay, what is the expression we are getting? So that is T2 is equal to, okay, for this pair 1 comma don't care. For this pair, horizontal side 0, 1 is there. It belongs to Q1. Both bits are different. Simply we have to ignore them. In the column side 1, 0 is there. So this one belongs to Q2 and this 0 belongs to Q3. So Q2, Q3 bar we are getting. Next one. For this pair, okay, we are considering horizontal side only one is there, this one belongs to Q1, and column side this column and this column we are considering. In this one the first digit is 0 1, it belongs to Q2, both bits are different, we have to ignore them. The second bit belongs to 0 0, both bits are same, we have to consider that one. Q3 value 1 means it is Q3. So Q3 value 0 means it is Q3 bar. So now common Q3 bar. So we have to separate Q3 bar, then we are getting Q2 plus Q1. Okay, next we have to find out the Boolean expression for T3. So observe the T3 column and write the ones and don't cares. So here 6 ones are there, so we have to write 6 ones. At two combinations, don't care combinations, 1 1 0, 1 1 1, we have to place don't cares. Whenever the three variable Karnaugh map is filled with ones and don't cares, so simply we have to write T3 is equal to 1. So T3 is equal to 1. So these are the simplified expressions for T1, T2, T3. Next, in the last step, we have to draw the logic diagram. In that logic diagram, in step 1, we already know that 3 T flip-flops are required. So this is T flip-flop 1, T flip-flop 2, T flip-flop 3. For T flip-flop 1, the input is T1 and the outputs are Q1 and Q1 bar. For T flip-flop 2, the input is T2 and the outputs are Q2 and Q2 bar. For T flip-flop 3, the input is T3 and the outputs are Q3 and Q3 bar. And here the same clock can be applied to 3 T flip-flops at the same time. Here we have to use negative edge triggered flip-flop. Next one, negative edge triggered clock pulse we have to apply for 3 flip-flops at the same time. And for the flip-flop 1, the output is Q1, it can be treated as MSB. For flip-flop 3, the output is Q3, it can be treated as LSB. For flip-flop 2, the output is Q2. Now what are the T1, T2, T3 values? Okay. Now T3 value is equal to 1. Here we have to write T3 input value is equal to 1. Now next T3. Next we can go for T1 is equal to Q2 bar, Q3 bar. Okay. So here this is Q2 bar is there. This is Q2 bar. This is Q3 bar. It can be passed to 2 input AND gate. Okay, so this is Q2 bar and this is Q3 bar. Whatever the output we are getting, that output can be passed to T1. Okay. So T1 is equal to Q2 bar, Q3 bar, Q2 bar, Q3 bar. Next one, T2 is equal to Q3 bar into Q2 plus Q1. Okay, here Q2 plus Q1, I am taking, this is Q2 and this is Q1. These can be passed to 2 input OR gate. So we are getting Q2 plus Q1. That can be multiplied with Q3 bar. So already it is Q3 bar here is there. So I am taking another one. So here, next this is Q3 bar is there. These two can be passed to two input AND gate. So whatever the output we are getting, that output can be passed to T2. Okay, so this is Q3 bar and this is Q2 plus Q1 that can be passed to two input AND gate. Whatever the output we are getting, that output can be passed to T2. So this is the logic diagram for mod 6 synchronous down counter. Okay, so I hope all of you understanding this video. If you really understanding this video, please click on the like button and share this video to your friends and classmates. If you have any doubts, please put your doubts in the comment section. I will try to clarify your doubts. If you really like this video, please subscribe my YouTube channel. So Divvela Srinivasara. After subscribing my YouTube channel, click on the bell icon to get the future updates in my YouTube channel. For better understanding of this entire digital electronics course, ORR DLD course, ORR STLD course, go to this channel and go to the playlist called DLD, ORR, STLD, ORR Digital Electronics. It contains approximately 340 videos. For better understanding, please watch these videos. Thank you. Thank you one and all for watching this video.